believe I didn't swap. All right.
So, yes, we've already eliminated these two. Sorry, the recording's delayed. So choice A is not it, and choice C is not it. Now, choice D that we're looking at now. If I drew any function here, okay, so draw some sort of a curve. It doesn't matter what the curve looks like. At some point in time, the derivative slope is going to be 3. Because the secant slope, look at the slope of the secant. Delta y is going to be 9. Delta x is going to be 3. So the slope of the secant is really 4 minus negative 5 over 1 minus negative 2, or 3. The slope of the direct line from this point to that point is 3. If the slope of the secant is 3, then the slope of the tangent has to be 3 somewhere. And then take a look. Right here. That looks like a slope of 3, right? That looks like a slope of 3 over there. So this is also true. So choice D is also out. Choice E. There exists a value C in that interval such that f of C is greater than f of x for all x. For all x. Okay? What does that mean? Don't look at the answer here, in our word. But if something is greater than it for the whole value, what does it become? What do we call that when it's the biggest?
Max.
The max. So pretty much they're saying there exists a point on this interval where there's a max. And there definitely exists a point on the interval where there's a max. If I looked at this function that I have here, here's the max right there. But if I drew any other function, you're still going to have a max somewhere. Take a look. Draw any function whatsoever. If I draw a function like this, there's still a max. There's your max right up there. So all they're saying is that there's going to be a max somewhere. Whenever a function is continuous and differentiable, you'll have a max. So choice E is also true by default. So choice E is out. Now, let's go back to choice B and prove that one. Choice B says there exists a point C such that the derivative is 0. When the derivative is 0, what kind of a tangent line is that? Horizontal. A clear exhibit of this one looks like it does, right? There's a horizontal. But this said could be false. Somebody give me an example of when this would be false, when there would not be a horizontal tangent. A linear function. Very good. Connect these two. Is there going to be a horizontal tangent on there? No. So the simple case is this one. Remember, the problem here says could be false, not must. Must means for all things. Could means come up with one answer that's false, and then we can consider that the answer.
That's pretty hard.
Okay? It's not an easy problem, guys. This is not an easy one at all. This is one of the toughest ones on the test. Okay, and notice it's on the calculator part. Would a calculator help you here?
Maybe.
Really?
Maybe. If I remember it. If I need a little function.
Yeah, maybe. Maybe if you had some notes in your programs and stuff, that would help. Okay, if you wrote down what the Unit theorem was, but it's not going to help you. So take a look. There's not necessarily a point C that has a derivative equals 0. This would be indicated by a horizontal tangent, which may or may not exist. Okay, again, this has to do with the fact that if you connect these, they might look like this. There's no horizontal tangent really. Maybe at the top there. If I connected them like this, there might be one there. But the easy example to prove this false is a linear function. If I drew it like this, then yeah, there is a horizontal tangent. And here there is one also. But what would be the max?
Would that be your max?
She's still gonna give me 7 cents.
The max for either of these would be this point if you drew it that way. Yeah. The max would be the upper part. All set? So if you drew it like this, Karen, that would be the max up there. Yeah. All right, 81.
Yeah.
All right, now, first.
So, if they had given you a definite function, they would have said what it would be called. That must be good. They would ask you like what exactly is false.
Which of the following is false based on this function?
Yeah.
Yep.
The reason why is could be is because they never gave you a definite function.
And that's where you have to think of all function values, all possible functions. Okay?
So it could be
Now,
a radical.
what I want to really quickly note, guys, when I was doing the solution, I totally forgot that this was a calculator section. I did it all by hand, and you can tell that it's a bit of a mess by hand. So I'm just going to show you the calculator solution. I realized after. I was like, wait, it's a calculator, okay? So I did this solution. I did all this work by hand, and I got the answer, but then I was like, wait, it's a calculator. So let me just do it this way instead.
How long did it take by hand?
A while. That problem took me like 5 or 10 minutes to come up with this. I mean, you take a look here. I'm talking about, well, what I did was I discussed the fact that this is only going to be 0 when this is n pi, where n is equal to 1, 2, 3, because sine of 0 is 0, sine of pi, sine of 2 pi. And I solved it all by hand, coming up with these two limits, and then coming up with an answer. But that was really messy. You would not be expected to do that by hand. So let's look at the actual answer this one.
Like it cuts in like more than half.
I know, it wasn't worth it by hand. Let the function f with the derivative given by f bar of x equals sine of x squared plus 1. How many extrema does f have on the following interval?
Look at it.
First of all, what are extrema?
Your
Oh,
max
Max and min, or critical points, right? Max and min we're looking for here.
I said it.
Be careful. So, the question says, how many relative extrema? So how many relative max or relative mins exist? When do I have a max or min? When the derivative equals 0. When the derivative equals 0. So, we use the calculator to graph f prime of x and see how many roots there are. Because this is the derivative. Look, they give you the derivative here. So go ahead and plot this. Go ahead and plot this. Okay, look to see how many roots you have on the interval between 2 and 4. So I'm going to do it together so we're all clear. Again, not intersection, but roots.
Across the, yeah.
Sure, intersections of the x-axis and the curve. It's fine. But there's no other function for this to intersect with, Kenny. That's why I'm saying not intersections.
Yeah, I know, you're right.
So I go here. I plug in sine, parentheses,
I assist you.
x squared plus 1, close parentheses. Okay, now, everybody, please look up for a second. Stop what you're doing. The interval given here is what to what? So do not graph the whole thing. Just graph 2 to 4. Okay, please, please. A lot of people are doing this. So 2, 4. Now, I encourage you, listen carefully, don't use negative 10 to 10. Use negative 1 to 1. Because I care about the intersections of the roots. So I want to zoom in on the x-axis. So graph that, please.
We know this is a sine and
Okay, graph that. It makes it a lot easier for you. What's the answer, guys? 4.
Or,
4.
an alternative, you can just graph the original.
Take the integral, you mean?
No, just graph the original.
Damn.
Once you're given, just look at the next minute.
So Mr. Hollis 10 minutes like.
Oh, use fint on your graph calculator? How are you going to graph the original? Not given.
Actually, no, I did the integral.
The problem is that this, Edgar, the integral of this is going to have a plus c at the end. How do you know what c is? It actually doesn't matter because it was just 200 to share, so it's still the same amount of max and mins. But don't do that, it's too much work, okay? I'm trying to teach you the short way. What Edgar did is he said, I'm going to graph the original and see how many max or mins there are. But if I just simply graph the derivative and find out the roots of the derivative, there's 4 roots there. But you can graph the original, or you can graph the original. The way to graph the original, if you wanted to graph the original, you go here, go to math, go to fint. I'm telling you how to do this without graphing on paper though, okay? Use y1 here. This is what Edgar did, everybody. Comma x, close this. Turn off the derivative. Okay, so he graphed the original, I think you solved by hand, right? He solved for the original by hand and then plotted it. I would do it this way if you wanted the original. Hit graph. What's the problem here? Why is there an error? Did I not close my parentheses?
No, you don't need a parentheses.
No. Here's the reason why.
Because the domain.
You can't numerically integrate this one. There are certain functions that are going to give you errors. You cannot numerically integrate this. And it has happened with nderiv also. And I put a little note. I think it was like a few problems after this. I'm going to talk about that also. So it would not help to graph the integral on the calculator. You did it by hand and you want to do it, that's fine. But again, the simpler way, graph the derivative, find the roots. Okay? But again, this normally works, but sometimes when you do an integration, you cannot have the integral of it. And I'll explain more of that later. Okay, but sometimes you're going to get an extra error there.
Is that too complicated for you?
No, it's because there's a discontinuity in the graph. That's the problem. Okay, there's a problem with the discontinuity. All right? Let's go to, what about 82?
And you just got that.
Right?
All right, 82.
I'm bad right now.
So, the rate of change, everybody, what is that? Derivative. We're on 82. The rate of change, back to your packet.
Oh my god.
The rate of change of the altitude is given by the following function. So, everybody, right away, please, the rate of change here is R of t. This is the derivative they're giving you. They're giving you the derivative. They're giving you the derivative. Underline the words rate of change, please, and write derivative if you don't have it. Again, rate of change is a derivative. Next, which of the following expressions gives the change in altitude during the time 0 to 8? During the time 0 to 8. So, if I want to know, I'm sorry, not during time 0 to 8, during the time the altitude is doing what? Decreasing. When is the altitude, or when is the rate of change, or when is the original function going to be decreasing? If the derivative is negative. So what I need to do is start by plotting this and find out when the derivative, when the actual derivative function is going to be decreasing. So let's take a look. So I go to my y equals, and I'm doing all this together, guys, because I know we're having trouble here. Let's plug in t cubed minus 4t squared
Plus 6. I don't think that
plus 6. Thank you. So again, this is the derivative. So when the derivative is a negative, the function is decreasing. So we need to figure out when this function is negative. I'm going to hit zoom. Well, I'm not going to zoom 6. I'm going to go from 0 to 8. And I'm going to go back again from maybe, let's say, I'm going to do negative 10 to 10 this time, just because I don't know what the function is going to look like yet. So take a look at our function here. All right. So clearly, if this is the derivative, this is the graph of f prime.
Negative when it's under the x-axis.
Very good, Kenny. So from here to here, f is decreasing in this location right here because the derivative is negative. Again, this is the graph of the derivative. When the graph of the derivative is below the axis, the original function is decreasing.
Wait, but how?
When is the original function increasing?
everything else.
Very good. Everything else or above. So the graph of the original is increasing from there, and whatever this goes out to be, I don't care what it looks like. Okay, so f is increasing for all other values. So what am I really focusing on? What do I need to find?
The roots?
The roots of the derivative. Very good. This is the derivative. I want to know the roots so that I can see when my original function begins to decrease. And if I were to do it this way, guys, remember my number line? This is what's happening here. That's what's going on right now. The derivative is positive. The derivative is negative. The derivative is positive. So it's an increasing function, a decreasing function, and an increasing function. Now, I have to figure out what those roots are, but look at your choices, people. Do you really have to?
No.
Look at the choices. Which one can you rule out right away?
Zero.
Okay, you can rule out B and E. Because at 0, everybody look. At 0 and C. Sorry. B, C, and E. Absolutely. B, C, and E are out.
Also,
Now,
D.
look at A and D.
D is off.
Look at A and D here.
Derivative.
Making a mistake.
No, I'm talking about
R. What?
D is out.
Oh, D is out. Very good. Why is D out?
This is derivative.
Because the RT is already the
Derivative.
R of t is already the derivative. So to find the overall net change, remember this whole thing we did with the pumping oil or the people entering amusement parks, how many of them enter and leave? It's the integral of the derivative. But the derivative is R of t. So choice A is your answer here. Choice D is the common mistake here because people see, oh, it's integrate the derivative. But R prime of t is really the second derivative. The second derivative.
So if we were to look at argument, we wouldn't necessarily need to.
No, you don't need the intersections. All you got to do is look at a quick sketch of the graph. That's it.
No, like not even that. Just looking at your answers.
Yes, you're absolutely right, Edgar. Edgar, say that again. Explain what you're about to say, because I know what you're going to say.
What is that?
Listen to what he's going to say.
He doesn't remember.
Right.
Pressure.
Here's what I would say. Here's what I would say first.
Is that what everyone say too?
I would rule,
I guess.
everybody look at choice D and E. Choice D and E. Rule those out right away, because you would be integrating the second derivative, really, right? Again, R is already the derivative. So you can rule out D and E automatically. Then you have to really look at the graph, though, still. Because you don't know when the function is decreasing. You have to look at the graph to see that it's decreasing between 1.572 and 3.514.
From there, you wouldn't even have to look at the intersections.
No, exactly.
From zero-
But you need to see a sketch of it still.
Yeah.
And you'll notice that the 0 ones, which are choice B and C, are out because the function is increasing at 0.
Yeah.
Okay? What's the other thing you could have done very easily?
I was really getting into details there.
What?
Oh, man.
Like,
Okay, find the zeros. That's what this is, Karen. Yep, find the zeros. But what's easier than that? Plug in 0 into the R function. What do you get? 6. Look at the R function. Plug in a 0, you get 6. So the function is increasing in the beginning, isn't it? But this asks for when it's decreasing. So right away you could have ruled out anything with a 0 also. You could have ruled out choices B and C and E without even looking at the graph. Because if you plug in 0, you'll see that the function is increasing in the beginning. Afterward, the function is going to be decreasing in 2 spots.
Sorry for interrupting.
That's all right.
oh, we're not just going to go to him.
Again,
I need a belt.
Wow.
if you typed in just R of 0, or if you just did R of 0, this drops off, you just get a 6, which tells you that the function is here to start. So if the derivative is positive in the beginning, it's increasing in the beginning. But this asks when it was decreasing. So 0 cannot be one of my limits because it's increasing at 0. Okay, so you could have ruled out the 0 choices also. But again, my recommendation, you're not going to see all that stuff right away. Graph it, look, see that this is 1.5 something, 3.5 something, which is automatically either A or D. Rule out D because it's really the second derivative. A is really the integral of the first derivative.
Isn't that not always true because it depends on the value of, like, in this case, 8. But it doesn't depend on that value and how it works in the function. Because it can, even if one of the integrals is 0, if the other one makes it negative, then it's going to end up negative because they're subtracting to each other.
Kenny, it says when the altitude is decreasing. The altitude is only decreasing when the function is negative. The function is positive.
No, I know that. I'm not saying that. I'm not disagreeing with what you said. I'm just saying that in other cases, when we have to look at both of them, it's not just 0, because that 8, depending on the function, could change it and make it a negative.
No. The 8 has nothing to do with it. What I'm trying to say to you is this. You can only integrate from one number to another when the function is decreasing. If one of the two causes it to be increasing, it's automatically out. Okay? The 8 actually caused it to be out also, now that you see the graph, had you not known that though. But when one of the limits means it's increasing, you can automatically rule it out, because we're looking for a decreasing. Okay? That's a good question. 83. All right, so 83 asks us. 83, I'm not going to put the answer up yet, because I know we're all going to see it. It tells us the velocity in feet per second of a particle moving along the x-axis is given by the following function. What is the average velocity? How do you find the average value of a function, guys? 1 over times d. Good. Very good, so that's it.
Wait, what is it?
Take a look, guys, that's it. That's all it is. That's what the problem, it says find the average velocity. They're given the velocity function, so they're saying find the average value. Remember we did this? Average value? Now you have to apply it. Okay? I'm not rubbing it, I'm just trying to make correlations.
Why are you putting the integral rule? Because
Average value of a function is 1 over b minus a times the integral from a to b of f of x dx, which is exactly what we have here. Okay? And notice it says, what is the average velocity? So we can do this because it's a velocity function. Had it said, what is the average position, we would have to integrate that, find a constant, and then do another integral with 1 over b minus a.
integral of position.
Position?
Yeah, you just said position. Like there's no integral.
Time. There is no integral of position.
There would never be a problem with that.
He said.
No, I said if they ask you for the average position,
Okay.
you could technically do the integral of velocity to get position, then do 1 over b minus a of the integral of position. You can get a number, but there's no term for it.
Gotcha.
No? All right, so you end up getting 20.086, choice A. Again, are you going to do this by hand?
No.
Absolutely not. Absolutely
I
not.
don't think it's by
Let's
hand.
quickly do this. Ready? Watch what I'm going to do. 1/3, because it's 1 over b minus a, right? Start with 1/3. Then press math. You want to go down to f int, which is number 9? Nice memory, very good.
I don't know, 8.
F int of second e to the x. Actually, what am I going to do instead to make this easier, guys?
R is Y1.
Yeah, just plug it into y1, then just do y1 there. So, because you might have to do something else with it. E to the x plus x e to the x. That's my function there. So when I integrate, I'm going to integrate y1, go over to vars, y vars, enter, enter, y1, comma, x,
No, you're 0.
lower than upper than x, or x then lower than upper?
I think it's X then lower than upper.
Let's try it. I forget sometimes, guys,
Yeah,
too.
it is lower to upper.
X 0.
It's lower upper than x?
No,
Or x?
it's X lower upper.
Got it.
Close.
Thank you. So again, the integral from 0 to 3 of y1 with respect to x, this is like saying dx here, and this is saying a 1/3 in the front of it. Okay, it's 20.086.
And if you wanted to take the, but if you, instead of you didn't have this, then you put x, x, comma x, that's the entire function.
Correct, but you can only graph that. You can't do that on the home screen. Okay? Again, what he said just now was, all you can do is graph.
What? When you speak.
No, it wouldn't be him, it would be error. Try it. Same command, right? And instead of putting the limit, you said just put x comma x. An error, okay? Because your argument does not work that way. Now, just for a little side note, guys, the TI-89 does do integrals by hand, and it gives you actual values back. I think one of your programs does it too, am I correct? Doesn't one of your programs actually integrate stuff in terms of x? It doesn't? Okay.
Just I haven't. I mean, I'm not a program. I can't.
It's not worth your time. They're not going to ask you to do that anyway.
I can find derivative, backwards, taking, and like other things.
Okay.
I can do trapezoidal, Simpson's rule, average value.
So maybe like
Tokyo,
next week on Monday, you can plan a lesson for everybody?
Why?
This weekend, make a lesson and, you know, take the whole period and go over everything on there?
Well, you guys, this is different than we
Yeah, I still can't get.
Well, he can transfer everything to yours at least.
You don't have the wire.
We do have the wire. To go from calculator, yes.
He doesn't want to do it. He doesn't want us to get forced.
I mean, I don't know. Edgar, honestly, what would you say, seriously, question? What would you say, how many questions did you actually use those programs on? Percentage.
Well, how many did I get correct? That's
Man, we're calculating the whole time.
Well, I mean, out of the calculator section, how many did you actually, because you can't use the programs if it's not in calculator, right? It's not going to help you there,
I think
obviously.
I'm like 10.
10 of the calculator
Yeah,
programs?
and I mean, like I have like a program that gives you the derivative rules too, so you can also.
Okay, that might help. See, that kind of stuff might help. If you have the derivative rules in there and that stuff. But you guys can all do that yourself. If you go to program, you can make a program and type it in. You could say, product rule, A times derivative of B plus B times derivative of A. You can just type in those words. No way, I mean, do you want to see how to do it real quick? Program, go over to new, hit enter, title it something, it doesn't matter what you title it, hit enter, and then just press second alpha for alpha lock, and I would type in PR for product rule. Then I would use the colon, and I would say A times the derivative of B. So I might put like B caret or something, because there's no derivative symbol there. Is there an apostrophe anywhere? Anybody see an apostrophe? That's a comma.
One for you.
Okay, so I would just do this then. I would say A, and then I would use, there's a little quote here. See a little quote right there? So use the quote, A times the derivative of B plus B times the derivative of A. I know, it looks like the second derivative, so I wouldn't use that then. Maybe instead use this symbol, guys. But it's all up to you to remember what you use. You got what I'm saying, all right? You can type this in yourself. Then type in a quotient rule, LDH minus low D high minus HD low, HDL all over L squared. Okay, you can type all that stuff. Sorry, what are you saying?
I did all that in somebody else's calculator.
Yeah. This is the same thing I'm saying, guys. You want to see what it looks like on here.
There's more.
Okay, but it's the same general idea. It's just giving you the rules. But again, you cannot use these rules unless it's a calculator section. And the majority of the ones in the calculator section, you're never going to do the derivative by hand. So these rules aren't really going to help you.
Or I can finish early and review on that real quick while I'm waiting.
Technically, sure. If you finish the calculator section early and you want to review the derivative rules for the next section that's non-calculator, that might help you.
Sure.
But I really hope by now you know the basic rules. The ones that are hard to memorize are the arc 10 and all that kind of stuff. And you saw that last night in your packet.
Yeah.
One of the problems asked you for the derivative of arc 10, 1 over 1 plus x squared. So those are the ones you just have to memorize at that point. Okay, that's a little bit tougher. All right, let's go back to the problems. All right, that's that one. Let's take a look at 84. 84, a pizza heated to a temperature of 350, so it's starting at 350, is taken out of the oven and placed on a 75 degree, or in a 75 degree room at time equals 0. The temperature of the pizza is changing at the following rate per minute. To the nearest degree, what is the temperature after 5 minutes? Remember, people, the net change theorem tells me that if I want to see how much something changes by, I integrate the derivative. So after 5 minutes, I want to see how much this changes by. So take a look at my function here. This is the derivative in the blue box there. If I integrate the derivative, it'll tell me the overall change. This is the same problem as going into the amusement park. We did that problem where we said, how many people enter the amusement park? We did the integral of the rate of change. This is the rate of change of temperature. When you integrate it, you end up getting negative 237. That's how much the temperature is going to change by in the first 5 minutes. But what was the starting temperature?
350.
So take 350, drop that value off, you get 112. Again, just to make this clear, we did this today again with the fundamental theorem. This is the fundamental theorem here. If you want to know how much something changes overall, all you need to do is integrate its derivative. Because the integral and the derivative, remember what do? They like cancel each other out kind of thing? Okay, so this is really like they're canceling out. So when you integrate the derivative from 0 to 5, it tells you how much temperature has gone down after how many minutes? 5 minutes. From 0 to 5. From 0 to 5. Okay? Why did I add the 350?
Because now it's starting.
Good. It started at 350. So, what about that 75 degrees?
Room temperature.
What about it? Did we use it?
No.
So what do we call it?
Extraneous.
Very good. Extraneous. You're going to be given extraneous stuff in these tests. Especially the part 2s. Part 2s are going to give you a lot of stuff. You saw those problems. They're like, 2-3 paragraphs long sometimes. Not everything is going to be used. You have to think about that. Next page. 85 was awesome. 85 was awesome problem. Okay, before looking at 85.
How did I get that one wrong?
It said, yeah, right? Good. A lot of this is up here, guys. You can't really do math. You just got to look. So, it says, trapezoidal sum over approximates. So, start by drawing in your trapezoids on each of them. See which one of them over approximates.
For some reason, all my trapezoids are going
A.
perfect.
Let's make a correlation. I'm gonna teach you guys this one real quick. It's very easy. I'm gonna draw these on the board so we're actually. All right, so. All right, first, choice E.
Exact.
It's exact. Very good. When you fit trapezoids, look at the trapezoids, guys.
You already stated that.
Pick points.
Take it away that very good.
Pick points. Those trapezoids are going to be exact, so this is out right away. Next.
It has to be open.
So,
Yes, we want the trapezoidal sum to over approximate. So draw trapezoids here.
It's under.
Huh? It says over, guys, over.
yes. If a
Over.
trapezoidal
If a trapezoidal sum over approximates, that's all right. So look, when I draw a trapezoid here and I draw a trapezoid here, doesn't that over? Now, watch what I'm going to show you. It's going to be amazing. Here, draw another trapezoid anywhere. Isn't that going to over also? Why are these two over approximating? Because the functions are what?
Decreasing. Exponential. Decay. Increasing.
Because you made it that way?
Inverse. I don't know.
What is that called?
Parabolic?
Symmetrical.
Exponential.
Concave.
Concave? Oh!
What is this?
Look at the next two. Watch. Watch. Here. Put a trapezoid here, guys. What is that trapezoid going to do? And isn't that concave down? Isn't this one?
That's so amazing.
Isn't that amazing? So, here's what I want you to write down. Please write this down. Not on the page for me.
We've been writing
Write it on the
everything
page.
here.
Here's what we'll do. You keep these till the end of the year and get back to me at the end of the year.
I like that idea.
Are we clear?
Yes.
Okay? Keep all these though in like a folder. Don't put these in your binder. Put them in a folder so at the end of the year or after the exam, you get these back. So here's what you want to write down.
Like, you're just trying to bully you?
Log
Hit what?
You're just trying to bully you?
Can you just what?
You're just trying to bully you?
Can you just maybe we'll just have a big bonfire.
Right?
Yes!
They were saying make chemical.
We'll just make a big bonfire.
I like that.
And then,
No physical changes, chemical changes.
and then you know what?
Irreversible.
At the end of that bonfire, we're gonna have a Lola Prize episode.
Well, good, actually, yeah.
Yeah.
That'd be
We're
very
on
complicated.
fire.
It is a good point. We'll try that, that's a good idea. Alright, so,
Have the wrong time.
so for concave up, the trapezoidal
Big word.
is an over approximation. For concave down, the trapezoidal is an under approximation. So far, so good? Again, what did we just make a statement of? When it's concave up, the trapezoidal over approximates. That was our choice A and our choice D there. Now, we then have to look at the next part, because clearly we're going to rule these two out. Those are done. But now we have to look at A and D.
Start from the right.
What is the only difference between A and D?
Those increase, those decrease.
Very good. So now we're going to make a correlation with RRIM, I think it's, yeah, RRIM, and increasing versus decreasing.
Start from the right.
RRIM tells me to do what, Christian?
Right.
Start from the right. So, for this function, when I start from the right, take a look at my squares, here are my rectangles. Are they over or under approximating? Under, because I've got all this extra space in here, right? So when a function is decreasing, RRAM will under approximate it. What do you think LRAM will do? It will over approximate. That's for a decreasing function. If we have an increasing function, this function here is increasing, right? What's going to happen there now? Starting on the left, watch.
Oh, under.
Over.
Finally.
It has to be in the calculator.
I thought you were doing LRA.
yeah.
No.
Yeah, circuit program. Get back to you.
Well, I mean, technically, guys, if you want to write this stuff in a program, I have no problem with that. That's some pretty good stuff to write down. This problem does come up once in a while. So,
ever have a joke?
the RRIM, we're told RRIM under approximates. We're told trapezoidal over approximates. So the only time RRIM under approximates is right here, while the trapezoidal over. Choice A. Choice A. So you see how you analyze that, though? It's all visual there. All visual.
But I'm actually confused. Why is it A?
Because R, you want to get R, it says RRIM under approximates, right? Take a look. Here's RRIM drawn in.
So it's both the correlate. Okay.
When it under approximates RRIM and it over approximates the trapezoid, that's what they're asking for. And that's the only,
I thought it had to do with one. That's why.
you're looking at the overlapping of two
Yeah.
constraints or two restrictions. This has to happen and this has to happen.
That does if you use two different like trapezoidal and like the Riemann sums, would that give you an average instead of having to use all three?
Not really, no. The trapezoidal is not an average, really. It's the best approximation. But the middle ram is close to an average of left and right, assuming it's linear, though. If it's not linear, the average changes.
Right.
And that's what I did, by the way, guys. Take a look. Okay? Trapezoidal over approximates when the function is concave up. Ram under approximates when the function is decreasing. Okay, and that's what I gave the example of. Any concave up function, these are all over approximations. Any decreasing function, these are all under. So which one happens to have the function decreasing and concave up? It's only choice A. Does you see how I write that down?
Yeah.
For my solution? Increasing function is here, decreasing function is here, concave up is here. That's those two things right there. All right, next one. Next. This one killed me that some people have this one wrong. We just did this. I know it's inverse tan, I understand that, but at the same time, guys, you have a calculator. You have a calculator, right? So everybody should have been able to draw this sketch to start. I mean, come on, it says, ready, watch, let's go through this. The base of a solid region, the base, in the first quadrant, bounded by the y-axis. So I'm simply just going to draw green lines over it. Y-axis, the graph of y inverse the graph of inverse tan the horizontal line y equals 3 and the vertical line x equals 1. There's my region right there. That's all I've done so far. You can all do this stuff, guys. You can all do this. How did I do this on the calculator? Let me show you. I went into my calculator. I went into my y equals. I pressed second tan inverse of x. I think it's just x, right? Yeah. Next, I knew that my y value up top is going to be 3, and the x value on the right is 1. So I went to my window, and I went 0 to 1. Then I went from 0 to 3. Because again, remember the horizontal line was y equals 3, and the vertical line was x equals 1, and it says the first quadrant. So I have to start at 0. Now when I hit my graph here, I see that this is my y-axis, this is my line y equals 3, this is the line x equals 1, there's the inverse tan region. So this is my region that I'm looking at right now. Okay? I know, it's tough to see, but that's why I drew a sketch for you guys.
No, I'm talking about the line you drew.
Oh yeah, that's pretty poorly done. Sorry. So here's my region now. Next, it says, for the solid, each cross-section perpendicular to the x-axis. Perpendicular. So my cross-sections are coming out of the board, and they're going to be perpendicular to the x-axis, which tells me I'm going to be integrating along the x-axis here. So they're going to be squares, it says. So really, I've got a square coming out of the board like that. That's that square. Then on this part, I've got a bigger square coming out of the board like that. So if I want to figure out this problem, remember how I do this. I find the area of one of these squares times the height of the prism. The height of the prism. Okay, the prism being left to right. So if I find the area of one of these, how do I find the area of one of them?
Square.
I square what, Kenny?
You square the base, or whatever side you get.
Okay, so tell me, Kenny, now, what is this height right there?
1.
2.
Oh wait, but don't.
The outer.
3 minus 2.
What is it?
3 minus inverse 10.
3 minus inverse tan. Let's go over this.
Yeah.
The full height from here to here is 3. Do we all agree with that so far?
Yeah.
The full height is 3. The height from here to here is the inverse tan. So if you want this little leftover height that's here between them, you do upper function minus lower function to find the difference. So you start by doing 3 minus tan inverse. That's going to be the side of the square. Now, I want to know the area of this square, so I take that quantity and I square it. I take that quantity and I square it. And what am I integrating from? This is 0, this is 1. I'm integrating along the x-axis. So I have dx there from 0 to 1, and I get choice B as my solution. Again, remember, you need the area of every single cross-section, and then you just need the integral of that. The integral of the area. This is the area of one of those squares. And then when I integrate it, I'm finding the area of all those squares together, which is what gives me a solid. It's like taking those coasters and stacking them up, but stacking them along the side. Take coasters and stack them this way. Eventually you're going to get a cylinder, right? You take the area of all those circles and multiply by the height. Well, we can't just multiply by 1 because they're changing. That's where the integral comes from. The integral tells me that I can do this for a function that is angular or changing. Okay? All right. Let's keep going. 87. All right, so this is a bit of a long response also, so let's just talk about this one. First, the function f has the first derivative given by the following. What is the x-coordinate of the inflection point of the graph of f? What is the x-coordinate of the inflection point? All right, first of all, when do you get inflection points? So the second derivative equals, and it changes concavity or sine. Very good. So, what can I start by doing here? Find the second derivative, right? Taking the derivative of this. So, if I want to take the derivative of this, let's go ahead and look at our calculator. I start by putting in parentheses, second square root of x, close, close, whoops.
Wait, shouldn't you put the, wait.
Divided by, I'm putting the original in right now, and then I'm going to do the derivative in
Okay, I was
y2.
going to say, why don't you just put function of risk since you have the first derivative.
I know, I'm going to list it in y1, and then in y2 I'm going to reference it, okay? And then I'm going to put this over parentheses 1 plus x to the third. Close. I don't want to graph that though. What do I want to graph again?
Derivative. The second derivative.
Yes, this is the first derivative. I want to graph the second derivative. So turn this off, go down, and try your end derivative function here. What happened, Karen? Why isn't it working? No, you're right, Karen. I don't think it's going to work here. That's what I'm trying to show you guys. So watch. I go to end deriv, go over to y equals, go to y vars, y1, comma x, close, and I hit graph. What's the problem here, guys? Anybody figure this one out?
The two x's? I don't know.
Here's the problem. Look at your first derivative. Doesn't it have some values that would cause this to be undefined?
Yes.
Doesn't it have a denominator?
Yes.
The calculator is using a numerical technique to graph the derivative, but it's getting stuck. It's getting stuck when the denominator becomes 0. So if you look at your original function, let's go back now and look at the actual function. Where's the function here? Sorry. Where's the function? I didn't even write it down. Okay. In the original function on your paper right now, look at the denominator. The denominator can be 0. When the denominator is 0, it's undefined. So the problem is that the calculator is trying to graph the derivative, but it's getting a problem because it's getting this undefined part. So what I wrote was this. The inflection point occurs when the second derivative is 0 and there's a sign change. Next, put the given function f prime of x in y1 and make y2, and I started by putting dy dx, but then I changed it. Make it the end deriv. Then search for roots. Unfortunately, this will give an error since the second derivative is not defined on all x. Again, that's because when you take the derivative, you're still going to have some undefined parts in the denominator.
So if you had a range, it would actually work.
Say again?
If you had a range, like a domain, it would actually work instead of getting an all x domain. Like, could you
No, it's not going to work, Kenny, because the calculator wants to graph this for all values of x always.
That's why
If you were given a certain point, not an interval, but a certain point, you could have done it.
Okay.
If you did the dy dx function of x equals 2 or 7, maybe then you could have. Okay? Now, since all of our choices are from 0 to 1, since all of our choices from 0 to 1, let's make our window from like negative 0.1 to 1.1 and look at the original function, or the derivative. Okay, let's look at the derivative. Now, when the derivative has a max or a min, then the second derivative is going to be 0. And let's go through this. So let's go back to our graph, people. Go back here, delete the second one, and let's actually graph the first one. And we're looking on the interval from, why did I say 0 to 1? Any reason? Oh, our choices, sorry. Look at all of your choices here, everybody. Look at your choice in the problem. The smallest value is negative 0.278. The largest value is 1.008. So when I go to my window setting, let's just go for my window from like negative 0.3 all the way to 1.1. For now, I'm going to graph from negative 10 to 10, because I'm not sure what it's going to look like yet. And I'm going to graph the, oh, come on. There we go. Clearly, it's too close to the axis to see. So what should I do for my y? Don't zoom in, but just change your window settings, please. Do not zoom in. Zoom in is not a good feature on this, because it zooms in on the x and the y. Now take a look at this. So my x values were negative 0.3 to 1.1, because look at my choices. My choices don't go outside of there, okay? That's why I chose that. Now, think about this, and this is where calculus gets really tough, guys. What is this the graph of again? No, look at the product. Is it the graph of the original, the derivative, or the second? The first derivative. Now, if I want to know when the second derivative equals 0, that occurs when my first derivative has a max or a min. Think back. If you want to know when the original function has a max, if you want to know when the original function has a max or a min, you set the derivative equal to 0, right? So if I want to know when the derivative has a max or a min, it would be the second derivative equaling 0. So the location, which we don't know yet, but let's say here for now, this point right here will indicate that the second derivative equals 0. Because a maximum of the first derivative is really setting the second derivative equal to 0. How do you find the max of a function now?
0.
What do you do? Use the calc function on it. Don't do it by hand again. Watch, ready? We want to find that max location. Here we do. Ready? Second, calculate. You want to find the maximum. Go to number 4. Enter. You want a left bound, so let's press 0. Come on, guys, listen and do this with me. Don't just sit here. 0, enter for the left bound. For the right bound, I'll pick 1. For a guess, I'm going to pick 0.5. Hit enter. You don't have to. You can just press enter. I know. 0.4725, and take a look at choice B. Take a look at choice B. So here's what you should write down. Ready? Here's what you want to write down. A maximum of f prime indicates an inflection point of f, of the original. Again, we wanted to know the x-coordinate that has an inflection point of the original. Whenever there's a max of f prime, it means that there's a horizontal tangent, which really means that the second derivative equals 0. Again, when there's a max of the first derivative, the second derivative is really 0. Because there's a horizontal tangent on the first derivative, which means its derivative is 0. Well, the derivative of a derivative is the second. So when you have the first derivative at a max, you can say that the second derivative is 0. When the second derivative is 0, you really have an inflection point of the original function. And what else can you look at? The function is increasing, isn't it? Then what happens? It's decreasing, which tells me that if I graph a second number line, that's my 0 point at 0.4725. 47. So this is going to be increasing in the second derivative, and this is going to be decreasing for the second derivative. That's what my second derivative number line would look like. And what did we say? Inflection points occur when the second derivative equals 0 and there's a change in sign. This is the change in sign. The derivative of the derivative, again. Okay.
Well, I'm a little confused. Actually, I understand what we're doing, but I'm just confused about the negative part.
Okay.
In a way, isn't it not negative because...
Over here?
Yeah, because, I mean, you're looking at the first derivative, and it's above the x-axis. So from the certain point, from point...
Yes, Kenny, I'm going to stop you for a second. Yes, you're looking at the first derivative, but what I'm saying is, look at the number line we're graphing, Kenny, f double prime. When you're graphing the second derivative, you need to be looking at the slopes of the first derivative to get the second derivative. The slopes of the first derivative are negative over here, thus the second derivative is negative. The slopes of the first derivative are positive over here, thus the second derivative is positive over there.
You're talking about the slope, not talking about...
Yes, the slope itself.
Yeah.
All right, 88. 88 was such an annoying problem, by the way. I hated 88. Okay? And look what I ended up doing for each of these. It's really a mess. Let me just show you real quick. So, first of all, we all know what's being asked here. Everybody, what is it? What are they asking us for? Look at the formula. The what? The average value. 1 over b minus a, integral of a to b of f of t dz. So, we are being asked to find the average value of this function. Now, if the average value is 1, it means that this stuff would settle out to be 1. So what I did was this. First of all, choices A and B are not correct right away because we can't calculate these values. Look at choices A and B. How are you going to be able to figure out, like here's what I did in my mind. Where's your pen? What I did was this. I took the 1 and I went across like this, guys. And then I took the 1 and went across like this. Now, take a look at this problem here. This that's above, this is above, this is all down here below, this is down here above. This is not splitting it into two separate parts that are equivalent. Here, this is splitting it into like a little part up here and a big part down below. So look at the rest of them. If I cut this one across right here, how could the average value of that one be 1 if the value of the function is above 1 for all values? If the value of this function is 1, then 2, then 3, that doesn't make sense, right? So this one is also out. Here, though, I can see that it kind of looks like it's splitting it. I don't know yet. And then finally here, if I look over here, what's the average value of this one going to actually be? Or what? How do you find average value, guys?
1 over...
You might say, which is 1/2, right? This is 1/2.
So...
1/2 times the integral.
Yeah.
What's the integral of this, guys? Do the integral of that region right there.
Oh, sorry, I'm done. Yeah.
Geometrically. What is the integral? Because the square is what?
It's 2.
2 by 2. Take a look at the square drawing here. This is really 2 by 2 here. I have this on the board.
I'm really
I have this on the board. I'll show you up here now.
So,
Looking at C, D, and E. Looking at C, D, and E. The area shaded for this part is just 2. So the integral from 2 to 4 is 2. Are we clear on that? If you do the area of these triangles, this area, this one is going to be 1 times 2 divided by 2. So this area is going to be 1, this area is going to be 1. Thus that area is 2. Next, this area is 4. This area here is 4. Now, when I do the average value, it's 1 over b minus a. 1 over b minus a. So I want to do, what do I want to do to these numbers next? By 2.
Yeah.
Again, this is the integral. This is the part here. That's what that is. But you still need a 1/2 in front. So when you do 1/2 of 2, what do you get? 1, which is the average value. Here you would do 1/2 of 4. Here you would do 1/2 of 4. Again, the average value is 1 over b minus a, which is your 1/2, times the integral. But the integral is just the area. This does not work. It doesn't check out. Is it 5 o'clock already?
Yeah.
Oh my gosh. What number are we on, guys?
89.
We need to get to the part 2s.
89. Hold on. Let me see. 90, 91, 92. Oh my gosh. All right. We'll stop here. All right. Let's just really quickly discuss one thing. What I asked you guys to do last night was the practice section 1 through 28. Okay, 1 through 28. I gave you the solution of that. I really want you to look at those on your own tonight. Because what we're going to do is tomorrow we're going to still continue with this and go on to part 2s here. So we're still not going to go over that. That's why I gave you the solution. What I want you to do tonight, or you have tonight and tomorrow, is the next multiple choice section with the calculator. This is the next part of what you did last night. So you can use a calculator. Use what we just did today, please, to help you. So work on this in the next 2 days. Yeah, guys, I'll put this on Facebook. I can post that. That's fine. I'll post the solution of this on Facebook and on Edline. Tonight you're working on this, okay? Tonight you're working on calculator section.
Hey Chris, I'll meet you in front of a couple minutes.
Anybody know anything about Houston?
Like where he is. Here's your 5 minutes.
Yeah, I'm here.
What about